Our project is the Perfect Thrower. The concept of our project was to create a treat dispensing ball launcher to keep dogs entertained while their owner is away. The device works with a series of sensors and motors triggered throughout the device, starting with the IR sensor on top. The IR sensor tells the machine that the ball has been placed in launch position. This triggers the treat dispenser to release a treat. Then the ultrasonic sensor sees if there are any obstructions. If the path is clear, the servo motor moves aside, allowing the motors to begin spinning the rotors. The ball is then dropped down and launched, and this continues in a loop until the device is turned off.
Next, we'll be talking about the components of our system. We had 5 primary types of components. The first is our IR brake beam sensor at 3 millimeters. This was used to detect whether or not a ball was in place. We also have our stepper motor and the ULN 2003 driver board that works with it to dispense the treats. Basically, that's to control our full revolution. Third type of component was an ultrasonic sensor, which we used to detect the distance and obstacles. Our fourth component was a micro servo motor, which was used to drop the ball and then would reset its position after dropping the ball. And we had our fifth type of component, which is the PMDC motor and the L298N driver board that was used to control both motors to shoot the ball. Next, we'll be doing a brief breakdown of our software code. So looking at the right at the workflow, first we would start the program and it would enter into a while condition. The while condition would then be checking for whether or not the IR is broken. If the IR beam is not broken, then it would return to the beginning of the while condition. If the IR beam was broken, then it would move to the next stage of the code, which is sleeping for half a second. Then it would dispense a treat. The treat dispenser would complete one full revolution, and then it would sleep for about 5 seconds. It would enter into a nested while condition, which is looking for whether or not the ultrasonic sensor was blocked. If the ultrasonic sensor is blocked, then it would keep repeating the while condition, basically making sure that there's a clear path for the ball to travel without hitting any object. Once the checked block returns false, then the program will sleep for 1 second and will enter the run motor function. In the run motor function, the motors would begin spinning, the servo motor would drop and then go back up, and then the ball would go through the motors, and the program would continue iterating until the user manually stops the program.
The manufacturing method that we decided to go with for this project was additive manufacturing. In particular, we wanted to go with 3D printing due to its advantage and flexibility of manufacturing for rapid prototyping and decreased costs in creating a one-off prototype. This influences the design for manufacturing and design for assembly to implement more complex geometries that would be much more expensive and harder to do using methods like subtractive manufacturing. We chose to go with PLA for this, compared to PETG or ABS plastic for its relatively low cost and ease of manufacturing. However, PLA does suffice in its structural rigidity compared to these other thermoplastics. That being said, our greatest concern for this structure were these features of blind holes with threads, as they held in the motor, ramp, rotors, launcher, which all exerted external forces onto the structure itself. We wanted this to last without having the external forces overload the structure itself. So I decided to go with heat press inserts that are made of brass that must be pressed with a soldering iron at a temperature higher than the thermoplastic, which is advantageous since metal has a higher tensile strength and tensile yield compared to PLA, which means I wouldn't have to suffice the geometry and design for manufacturing, but still have a stronger thread that's much more reliable and durable. Some assembly techniques utilized in this build was using interference fits to join the base together, being produced in 2 pieces. It uses a dowel and a hole to be pressed together, but also utilizes thermoplastic welding to create a more permanent bond around the joint. I also utilized RTV red stuff gasket maker along this motor mount to help dampen the secondary vibrations caused by the motor that spins at very high RPM, 10 to 20,000. Complications we faced during the semester with this project entailed both manufacturing and design, such as creating various revisions, like the housing or different rotor sizes for better optimization of how the printed parts work with the ball itself, in addition to the code, and things like different design plans compared to initial plans, such as utilizing different hardware, and also experiencing complications that are just unique to 3D printing and additive manufacturing itself.